So welcome to the final colloquium of this academic year. We are glad to have Professor Mononita Chakraborty from IIT Indore today. Mononita, like most of our speakers, did her undergrad from Presidency Physics between 2005 and 2008, and then went to TIFR as an integrated PhD student. At TIFR, Mononita worked with Sudhir Bhattacharya, who is an expert on neutron star and other compact objects. Some of you may remember that Sudhir was also a speaker about 1.5 years ago. Anyway, after finishing her PhD at TIFR, Mononita was a visiting fellow at IUTA for a short period and then postdoc in Istanbul. Istanbul happens to have a very good extra binary compact object
pulsars
community. Yeah. Because I remember in 29 or somewhere, there was maybe before, there was a big conference.
Yes.
So after finishing her postdoc, she came back as an inspired faculty fellow at IIT Indore and then continued as a permanent faculty member there. And so Mononita is an expert on neutron stars and pulsars and related other astronomical objects, and also now in pulsar timing. So, Mononita, please.
Thank you. Thank you. Yeah, that's so thank you to Ritavanda and Shuchitanadi and everyone for giving me the opportunity to talk here. It's an amazing pleasure and honor to be here because this is my home. Yeah, but today I will be talking about, neutron stars, which is something very close to my heart, and different manifestations of neutron stars like pulsars and some very exotic kind of pulsars. So I will try to give a brief glimpse of, these different objects and whatever the kind of things that we are doing in our group. So if you have any questions, please feel free to stop me. This is my group. So in my group, I have different directions starting from black holes to neutron stars. But today I will be talking about the ones in blue only, not black holes. And this is what we are talking about. So we work a lot on neutron stars. When I say neutron stars, I mean these are not pulsars. These are mostly neutron stars which are in binary systems with a companion. We'll talk about them a little bit more in detail later. And then we have pulsars, and pulsars have all these three classes. Primarily today we'll focus on this canonical radio pulsars and magnetars. So what are neutron stars? First, I should give a little bit of introduction since there is some MSc students also here. So neutron stars are basically remnants of massive stars. Massive stars, I mean 8 to 20 times the mass of our sun. And when they die through supernova explosions, this is what is left. These stars, the beauty of this star, remnant stars is that they are, about 1.4 kilometers in mass, but kind of squeezed into 10 kilometers. Imagine, slightly half of Calcutta or something like that. So that means that the density at the core of this neutron stars reaches very exotic conditions. What do I mean by exotic conditions? I mean that the density is much higher than the densest thing we know of. What is the densest thing we know of? That is the nucleus of an atom. So, but inside neutron stars, the core of neutron stars, the density reaches conditions even denser than the nucleus. But the temperature is relatively colder. So you have superconductor at, forget about room temperature, much higher, temperatures you have, superconductors and so on. And typical densities are nuclear densities. And the other cool things they show is basically they have a very rapid spin. So some of these stars can spin about 600 times in 1 second. And they have a very high magnetic field. When I say high magnetic field, I mean about 1 trillion times, at least about 1 trillion times than the standard Earth or Sun magnetic field that we know of. So why are we interested in them? One of the key reasons we are interested in them is this dense matter at the core of the neutron star that I was talking about. And we don't know what exotic form of matter happens at such large densities. We know neutrons, protons are made of quarks, right? But if you keep increasing the density, what happens at these quarks are no more bound together to form neutrons and protons. They become free, which is typically what we don't see in laboratories. And that means we have a exotic state of matter, which we cannot even, particle physicists cannot even recreate in their laboratories. So what we do is we hypothetically propose some equations of state of how this matter would behave. And in this diagram, which is the mass radius diagram of the neutron stars, this solid line shows this hypothetically proposed behavior of matter. But observationally, what we want to do is measure the mass and radius of this neutron star, which is this, lines that you see. These lines are basically mass measurements of certain neutron stars, and that can constrain some of these solid lines, which are the theoretically proposed neutron stars equations of state. And thereby, we would be able to understand how this exotic matter behaves. Yeah.
So if the mass radius relation, these are different equation of state,
right.
in what aspect? I mean, these are nuclear matter and they're different.
Yeah.
So for example, any clue, like what could be the equation of state? Like let's say one of these green or blue lines.
Yes. So the green lines are typically this strange star equation of state, which basically means it's predominant by strange quarks, along with not just uniquely, but along with many other exotic hyperons, lambda particles, and so on. I'm not a particle physicist, so I cannot give you the very details of it. But yeah, basically you come up with different combinations and different Lagrangians of these particles, and then try to solve for this particle equations of state.
Then you have a population and
exactly. Mass radius. Yeah, because mass radius is more measurable than pressure density. Yeah. And the blue ones are the more nuclear physics equations of state, like not so much strange quarks, but you
so
have.
How do this? I think what she was originally asking related to the equation of state.
Right.
How do they look like? They don't look like polytropes, right? They look like something else, or they look like some other exotic.
So yes and no. So depending on what you want, you can come up with a very complex Lagrangian. And if you there are situations where the Lagrangian can be such that you can break it down to piecewise polytropes.
Thank you. That was actually my question. So one more just
sure.
You. I mean, the projector is here, so it might, because the light is getting blocked. So can you just keep that side?
Oh, this side.
Yeah. This
side. Sorry, very sorry. I have this bad habit of pacing about.
No, moving is fine.
Yeah. And on this side, what we have is basically the curvature as a function of the gravitational potential for different objects. And you can see that the neutron stars here, they are kind of occupying the most, curvature phase in this particular phase space, which basically means that the gravity can reach very strong field regime conditions for this particular neutron stars and, X-ray binaries. Basically, when the neutron star is with a binary companion. That means that you can test different theories of gravity close to this compact object, close to this neutron stars. And obviously, extreme magnetic fields is something which we'll talk about in more details later. So that helps us, gets motivated to study neutron stars. One particular subclass of neutron stars is this pulsars. So what are these pulsars? So these pulsars are typically a subclass of neutron stars having a very high magnetic field. What do I mean by high magnetic field? Typically 10 to the power 12 to 10 to the power 13 Gauss. And you can think of them to be a kind of a bar magnet, a dipole bar magnet. And this is their rotation axis and this is the magnetic axis. So they rotate, and like a dipole radiation, there is dipolar radiation along this magnetic axis, which kind of sweeps about. And like a lighthouse, when it cuts your line of sight, you will get a blip. So that's a pulsating radiation. That's why it's called a pulsar. This was supposed to be a GIF. I don't know why it's not working, but this is how a single pulse, of a pulsar looks like. Okay, fine. The good thing about this is this canonical pulsars. These are called canonical pulsars, and they are mainly, their radiation is powered by this rotational energy. So they are rotating in a very strong magnetic field, and that's what resulting in this strong dipolar radiation. This is basic Griffiths level electrodynamics. But the good thing about this is they are extremely stable rotator, number one. Number two is, this high magnetic field gives them very dominantly emitting in radio. So therefore, we can use them to study physics of high magnetic fields as well as use them as the best clocks in the universe. Fine. What can we do with them? We can try to understand their physics. Now, when we say understand their physics, what can we do with them? One of the key things we want to do with them is these field things, test strong field theories of gravity, which theory of gravity is correct. It becomes non-degenerate in the strong field regime where the effect of gravity is higher. So you can test that with pulsars, you can test equation of state, and so on. But let's first start with the other block, which is basically trying to understand their emission mechanism. So pulsars were discovered about 60 years back by, oh my God, I had that discovery plot. Anyway, 60 years back, but we still don't know why they emit. We know the basic dipolar radiation, but the nitty-gritties, the details, the intricacies of pulsar emission is still, unsolved phenomena, unsolved question. So we want to understand what is the pulsar emission mechanism. And in this beam that I showed you, this particular beam, this is a beam, right? What is the geometry of this beam? Only when we understand that, then only we will be able to understand the physics of pulsars. So that's what we are kind of focusing on. So therefore, one of the things in my group, we were studying is something called single pulse behavior of pulsars, which basically means pulsar, these are kind of big lines are basically individual pulses of a pulsar. Normally, we don't do that in pulsar studies. Normally, what we do is because single pulses are weak. We average them, like thousands and thousands of pulses are averaged, and then we look at it. But if we have a good instrument, and if we have a bright pulsar, we can look at single pulse level. And if we look at single pulse level, then we can actually understand what is happening in the magnetosphere. So this is a kind of a snapshot of the different single pulses of the pulsar. And you can see that they show some modulation. There is not much regularity in this modulation, so let's call it unorganized modulation. We'll bring that back later. On the other hand, here, what we have is something called the organized modulation. So you can see that what we see here is pulsar phase, and this is time. So basically, different pulses are stacked. First pulse, second pulse, third pulse, fourth pulse, in this way. And what you see here, that the pulse peaks are kind of sweeping or moving, marching ahead in phase in a very zigzag, regular manner in this particular diagram. This is called organized modulation. And the more fancier name of this particular phenomenon is called subpulse drifting. And we study this subpulse drifting using these two instruments. Yes.
This is, so you get the signal and you post-process it in that way that you look at like organized.
Yeah, so basically, these are the pulses. So if you put these pulses, stack them up, one on top of them. So this is that diagram. Okay, this is one particular line here is basically one pulse period. So when you stack them, you see this zigzag lines, drift lines. So we studied them using these two very famous telescopes in low frequencies. The good thing about these are they are very good telescopes in low frequencies. On the left hand side, we have the Murchison wide field array, and on the right hand, sorry, I always confuse my right left. On the right hand side, we have the Murchison wide field array, and on the left hand side, we have our very own GMRT. This is the giant meter wave radio telescope, which is mostly what we have been working on with. And using this, what we can do is, because of its sensitivity, we can look at the subpulse drifting. Probably this will answer your question better. So what we see is that this is the pulsar beam. So if you are looking at the pulsar beam, you will get a pulsation when your line of sight, this is the red line, cuts the pulsar beam. Now, if you stack them up in this way, these are the different pulses. And as you stack them up, this is forming this marching ahead, zigzag pattern. And this is famously known as subpulse drifting. And each of these individual blips is known as subpulses because they are subsections of a pulse. Right?
What is the x-axis level longitude?
Longitude, because this is related to the rotation. So the pulse phase can be converted to the longitude of the pulsar. This is just a bad convention or bad habit of pulsar astronomers. We often try to express the phase in longitude.
Right.
So this is known as subpulse drifting. Now, why does subpulse drifting happen? The basic idea was given long back by Ruderman and Sutherland And the main idea was that the magnetosphere is basically a region dominated by magnetic field and electric fields. So what we have is a cloud of charges. And on these charges, because of this electric field, you have electric discharges, or what we fancily here call sparks. And what you have is eventually, because of the sparks happening here, if you take a cross section of this beam, pulsar beam, you will get a carousel, like a fairground carousel. You see in the fairs, you get a carousel of these sparks. And when they cut your line of sight, you will see this subpulses. Now, what happens is that the pulsar's rotation and the subbeam's carousel's rotation rate are different. So, since they are rotating at different rates, the pulsar rotation and the carousel rotation rates are different, which is resulting in this subpulse drifting when they cut your line of sight. This is what we are interested in. This is another diagram which shows, what is happening when this pulsar sparks are cutting your line of sight. And these are the sparks, and you can see the magnetic beam, which is also rotating, that is pressing out this subpulse rotation. Yes, subbeams kind of. So what do we call sparks? Exactly. So that particular spin is what we call carousel rate or drift velocity or drift rate. Is it drift rate? That's the question we are trying to answer. Okay. It's a very challenging question, and you will see that even that is, there are a lot of complications. Right. Exactly. Yeah. This is basically the the ground zero answer to that, but there are a lot of questions that we are trying to understand. So we studied one particular pulsar. This is one ex-PhD student of mine who studied a bunch of the subpulse drifting pulsars using GMRT. And you can see that for one particular pulsar, we saw 4 subpulse drifting modes. This is a snapshot of 4 modes. How do we understand there are 4 modes? We look at the vertical repetition rate of a particular subpulsar, vertical period, basically. And we see 4 different modes. They correspond to these 4 different profiles, pulse profiles at different frequencies. This is the lower frequency, which we call band 3 of GMRT, and this is the band 4 of GMRT. And you can see that the 4 different modes are shown by this pulsar. The other interesting thing is that from one mode to the other mode, the pulsar switched very rapidly, like almost, the span of one particular pulse. Okay. So why these different modes are observed? That's also, something we are trying to understand, how this mode switching happens that in the beam. So we looked at, the P3, which is basically the vertical number of pulses for one subpulse to come back to its original phase after shifting. So this is a P3, and you can see that vertical period is very different for the different modes. So the different colors represents a different mode. And here, the other interesting thing is that this pulsar was a nulling pulsar in certain particular pulses. What do I mean by a nulling pulsar? A nulling pulsar means a pulsar suddenly shuts off its emission for a particular series of pulses, and then it turns it on again. That's what we call a null. A lot of these pulsars are nulling pulsars. However, the interesting thing we see that for this particular pulsar, for a particular cases of nulls, they are very strongly related to one of those drift modes. It means that only when a particular drift mode is happening, then only when a particular set of nulls are happening, like immediately following. There is a strong drift mode to null connection. Okay.
Why do you have this kind of things, magnetic field, or what is the reason?
Open question.
Okay.
I said no, pulsar emission we don't understand. We are trying to understand nulls. There are 2 reasons, 2 very vague pictures that has been proposed. One is the pulsar starts off its emission. Why? Question, obviously. Another is it loses its coherence. Okay. So both can be very well possible, but null is still a very mystery to us. And there is some periodicity to nulls that have also been seen. So not our work. Yes. So nulls are kind of repeating at a particular period. So yeah.
Has it ever happened that it never came back after.
After a null?
Studying the
Not really. No, not that I know of. There are some pulsars which are intermittent pulsar, the other way around, off most of the time and suddenly switches on for a short time. So that if you interpret as never came back, then that may be. But nulls are typically, some gaps between the emission regions. But there are, cases of short nulls and long nulls. And this is what we looked at, that some of the short null occurrences are very strongly connected to one of those drift modes. So that means the reason the null is happening is kind of related to what is happening in that particular spark configuration of that particular drift mode. So that's what we shown, one of our, and we see that nulls are not complete nulls, particularly for the short nulls. If you add them up, you will see some low-grade emission. So that may probably, favor some of those decoherence theories. That it's not completely shutting off, but there is some decoherence happening which is weakening the emission, and that's why you were saying a null. But there may be possible that both kinds are present. And the other interesting thing we saw that this drift modes that I have shown you, they are coming from different emission heights. So here in this plot, what we show is the emission height of these modes, this particular modes are shown by these different colors as a function of frequency. So when we plotted that, then what we saw is that the P3, which if you remember is the vertical periodicity of the pulse to come back to its original phase, has an inverse relationship to the emission height, which basically means possibly the different drift modes are happening because these are originating at different emission heights in the pulsar magnetosphere. That's one proposition. So that's one of the very new things that we have shown here. And this is another kind of pictorial representation of the same. Here you can see that this is a two different spark configuration, and imagine them to be happening at two different heights in the pulsar magnetosphere. So that kind of gives an idea of why this may be the case. However,
but you assume at the same different radius or at the same radius of this that
no,
that the radius has changed, it will be the similar time.
no, the magnetic lines of force are not significantly changing, right?
I don't
Achha, you mean the radius of the carousel? That can be there. That can be
so
there.
that can compensate again that.
That can
So
compensate.
how do you fix the height of it?
So
Emission
yeah,
height.
so for the fixing the emission height, what we do is we do a polarimetric study. We do a polarimetric study and we try to find out from the polarization angles what is the angle between the the electric field and this edge of the magnetic beam. So if we have polarization data, those kind of things can be calculated. So that when we calculated emission height, that was, I skipped a little bit for the sake of time, but that can be calculated from solving the magnetic, having the polarization data and solving the magnetic beam geometry. Fine, all this is well and good, but till now what we have been talking about is basically very steady subpulse drifting. Now comes this particular pulsar. This is our favorite pulsar. This particular pulsar is suddenly rediscovered, I would say, in 2022. Why rediscovered? Because this is actually, to answer Ritubanda's question, was actually nulling most of the time, and only 77% of the time, and only emitting like the 30% of whatever, the remaining 1 minus 77% of the time. And that basically means that we missed it in most of the earlier surveys. Now, when we have sensitive observations and we are looking at single pulse levels, we are able to detect this, rediscover this pulsar. That's all well and good. But this was also a subpulse drifting pulsar. And in the non-Laring regions, when we looked at this subpulse drifting pulsars, the most amazing thing we saw is that not only like the previous pulsar, it showed different subpulse drifting modes, but also within a subpulse drifting mode, its behavior evolved. So what we are calling, as opposed to stable drifting modes, evolutionary drifting modes. Means within that particular mode, there was a gradual evolution of the phase shift. Okay, so that's is a very, very rare class of pulsars which are called evolutionary subpulse drifting pulsars. So that even questions further the ideas of subpulse drifting or this spark configuration that I have nicely shown you, the Ruderman-Sutherland model, because that doesn't, that cannot explain this particular evolutionary drifting pulsars anymore. So what do we do? So we looked at this pulsar using, again, GMRT, and what you see here is over different snapshots, the emission of the pulsar as a function of time. And the white regions are the regions where the pulsar was off, and the gray regions are the regions where the pulsar was on. And if we see the small chunk of this region in GMRT, what we see is this particular pulse stack. This is what we call pulse stack. Now, in this pulse stack, you can see these drifting modes. If you see them clearly, these drifting modes are slowly evolving further and further apart. Not only that, there is mode change, there is broken drift bands, and there is a lot of strong nulls. So again, we looked at this and we found four different drifting modes. But yeah.
So these are what different observations? I mean, each of these.
Yeah. So these three are one day, and this three is another day. But when we do GMRT observations, on one day we do different scans. So these three are three different scans of one day. These three are another three different scans of 10 days later, basically. So
the time period of this pulsar is what, 1.3 seconds?
1.3 seconds, I think. Yeah. So for this pulsar, what we saw is that there are four modes. Now, from these four modes, we have A0 and we have B. If you see this plot, you will be clearer what I mean. So this is B. And you can see that the drift modes, the white lines are basically, we have modeled the drift mode evolution. So the B mode is a stable drifting mode. So you can see that the drift shift modes model fits are very pretty straightforward lines. Similarly for A0, they are again similar, stable modes. But whereas as opposed to that, we have this A1 and A2 mode. Now A1 and A2 mode are very strange modes, which we are calling evolutionary drift modes. And where it's happening that for A1, the drifting is going from fast to slow, and for A2, the drifting is going from slow to fast. So, and A2, another key thing about A2 is often followed by nulls. About larger than 90% of the cases, it is always followed by a null. So that is very interesting because evolutionary drifting modes are very rare even among subpulse drifting pulsars. And when we looked at detailed modeling of the drift rate as a function of the pulse number, we see that obviously the slow to fast and the fast to slow, that thing is there. But within that also there is a lot of complex variation. So that means, there is a lot of physics happening in the magnetosphere, which is beyond the spark model or what we call the traditional carousel model, which is, making the drift mode doing a lot of dancing pattern.
How do you find out the mode? That's why you Fourier transform and getting some peaks there, or
okay.
how many modes are there, and how do you find out?
That's a very good question, and this is the question we have, we are struggling with because in the very early days, because this is a little bit, particularly for the evolutionary drifting modes, Fourier transform becomes a challenge. For the stable drifting modes, that's still okay. What you do is along the pulse stack, you do a what we call phase average Fourier transform, basically phase average power spectrum or PAPS. And that will give you a peak and you get that as a vertical repetition period. For this one, it's very challenging because it's an evolutionary frequency, right? It's not a stationary time series anymore. So what you do is these white lines that I was showing you, these are basically some evolutionary models of the frequency. Okay, so we tried with 2-3 evolutionary models. One is linear drifting frequency. Another is exponential drifting frequency, right? And then you fit it with that. So these white lines are basically showing that.
Then you are also assume how many modes are there.
Exactly. So it's a very difficult task at the beginning because you redo it, do a lot of, basically you change the boundaries and see which gives you the best possible solutions. Yes. Sure.
In case of subpulse drifting, how are the boundaries actually marked if there is already everything within the
Yeah.
modes?
Yeah. So it's a very important question. And what we do, as I was explaining, that we take a particular model of the drifting. Typically, there is a reason behind those ideas, reason behind those models. One, you take linear drifting. Another, you take, exponential phase drifting models, and you try to fit it. Now you look at some relevant statistics associated with those fits and change the boundaries. Now, when you change the boundaries, start with a good trial solution from visual inspection, but then you change the boundaries and you look at your statistics. Okay, and the statistics basically decide where you should stop. Okay, so basically the local features are even more complex, and that's basically means the magnetosphere is doing a lot of what I like to call dancing. However, remember one thing I kept coming back to is called nulling. Nulling means the switching off of the pulses. Now, this pulsar is a very strongly nulling pulsar. The curious thing is with GMRT, which is slightly higher frequency than MWA, we saw a slightly lower nulling fraction, about 58% compared to 77% with MWA, around 185 megahertz. And we saw a drift null collection where in about 90% of the cases, A2 was followed by a null. But the other interesting thing we saw is memory across nulls. That is the most amazing thing, because here you see this is called what we call refret memory. What does refret memory mean? It means that there was subpulse drifting, the pulsar switches off, and then it turns on. But when it turns on, it remembers what its original drift rate was supposed to be if it didn't shut off. So that is called refret memory. The other thing we have seen is called subpulse memory. It basically means the pulsar was rotating, suddenly apparently it stopped. And when it switched on, it started from the exact point where it stopped. That's what we call subpulse phase memory across
That
nulls.
is not the case for other nulling cases where
it has been observed. It's not the first time we have like for this pulsar, but not always. Very rare. It's difficult to find memory across nulls, but we are very excited when we find them.
Okay. Any reason that you have like 58% of the time the nulling, whereas it's 77? Is it like the sensitivity of UGMRT, or is it the frequency dependence? What would be the possibility?
I would say that I don't have a right now an answer. This is also something what we are trying to do. Obviously, see, with 3 observations, claiming big thing is difficult. There are reports of frequency dependence of nulls. So we have proposed future observations also, where we have tried to study whether this is indeed frequency dependence or a sampling problem. Because these are highly nulling pulsars. If 2 snapshots are taken, it's maybe, just sampling problems. But frequency dependence of nulls also have been reported, and maybe this is frequency dependence. So we are trying to, answer that question by more and more observations. Then only this will be clearer. Yeah.
These are is the using same pulsar, or they are further away from us? That's why you are observing right now the sensitivity. My question is, we have a lot of other pulsars which are bright enough to see the single pulse. Do we see such kind of phenomena there as well?
So only 10% of the bright pulsars do show subpulse drifting. 10% of the total pulsars, sorry. Total pulsars show subpulse drifting.
Not all of them. That's also you don't know why.
We have like very preliminary idea related to this whether what would be the best conditions to generate those spark subbeams. Because you need those subbeams to form for subpulse drifting to happen. So the pulsar electrodynamics decides whether those subbeams is formed, and that depends on the basically the beam geometry. Beam geometry and what is happening in the pulsar magnetosphere. But that's only a preliminary idea, and that's what we are trying to understand, basically. And Also, one interesting thing is that GMRT, particularly the upgraded GMRT, now have full Stokes data. This is a little bit unexplored thing. It has started relatively recently, and people are still trying to understand, its full potential. But full Stokes means it gives you observations in all the Stokes modes. That means you have the polarimetric idea of those radio observations. So whatever I am vaguely putting towards electrodynamics, some of them could actually be constrained using this polarimetric observations. So what we do it is not very recently, 2 years back, we did redid the observations with of these pulsars with full polar data and tried to get the polarimetric maps of the subpulse drifting. It's immensely difficult. It's immensely difficult because you have to have single pulses and you have to have single pulses in all the 4 polar modes, which means that you have to go down in sensitivity very significantly. So they are, struggling with noise is a constant fight, which you have to win. It's a very difficult problem, but then, for this particular pulsar, it being bright, we could do that. And this was done by a MSc student who looked at this different polarimetric behavior of the drift modes. These are the 2 stable modes, and these are the 2 evolutionary modes. What you see here, sorry for the small font, but what you see here is the ellipticity angle of the Stokes Ponca sphere. You have the position angle, you have the fractional linear polarization, and you have the fractional circular polarization. Okay. And these are for the 2 stable modes, and these are for the 2 evolutionary modes. So that's the polarimetric observation. And what you see is that the ellipticity angle showed very strong switching, particularly in the evolutionary modes. We also saw in the circular polarization, there is a switching between the handedness from right circular to left circular polarization along the drift modes. So it has some ideas about how the electric field vector along the subpulse spokes is cutting your line of sight. So that's what this is a little bit ongoing work, but we all saw that all the polarimetric behavior is very strongly drift synchronous. And we also looked at, for the memory across nulls, what would be the polarimetric behavior. And you can see that for the polarimetric behavior of the nulls, and when the sudden drift mode switching was happening, it also remembered its polarimetric behavior. That's what we saw. So memory across nulls is also preserved in the polarization space as well. Similarly, we looked at features where there is sudden drift mode transition, how the polarimetric behavior is changing when there is sudden transition from one particular mode to the other particular mode. And we saw is that one interesting thing is that there across this sudden change of the drift modes, the polarimetric behavior was not abrupt. It was kind of gradual. That basically means there is not a sudden, drastic sudden reconfiguration of electric field that is happening there. Yeah, please.
This is after you identify the mode.
Yes.
Then you sort the polarization.
Yes.
But if I do the other way around, if I get one of the polarization thing, if I try to reconstruct the modes, you will get the same thing, same mode pattern.
See, in theory, yes. In practice, one of the problems we were struggling is because when we are looking at particularly the QUV, the sensitivity is very low. Exactly. So there, finding the modes would be even more challenging and life would be much difficult. I is fine. QUV is more challenging. And this is a position angle switch. The pulsar's position angle, which is the polarimetric electric vector angle, is supposed to form a S kind of a curve. This is coming from the rotating vector model, if the electric field vector is rotating. But what we see is that for the stable modes, which is A0 and B, kind of the S is being kind of, traced out. But for the evolutionary mode, it's much more, wonky. So that is kind of telling you a lot of complexities in the electric field vector are happening when the evolutionary drift modes are ongoing. How much time I have?
Started at like
355.
Yeah.
Sorry, 255.
So,
Okay,
Yeah.
fine. So let me first end this story. So we have been talking about this, evolutionary drifting modes. So one of the big problems with the classical carousel model, the spark model that we started with, is basically it cannot explain this slow evolutionary of the drift rate and this rapid switching of the one drift rate to the other drift rate or one drift mode to the other drift mode. So what can be the possible solution or alternate to this? One of the alternate, not the only, by the way, one of the alternate we are proposing is basically two different scenarios can happen. One is this, this carousel is rotating. Now, if there is an ionic discharge happening in the magnetosphere, that will act as a screening mechanism in the magnetosphere. And this screening mechanism will change the electric field and the magnetic field vectors, and that will result in the change in the drift velocity. Okay, so basically carousel speed will change, therefore. This rotation speed will suddenly change, as you can see from this animation. So basically, one possible option can be there is a change in the drift rate that is happening, which is resulting in the evolutionary drift mode. The other possible scenario that can happen is, suppose we started with the n number of sparks in the carousel. Now suddenly, because of the changes in the magnetosphere, one extra spark is appearing, or one spark is disappearing. Means there is a change in the number of the sparks. So what will happen is that this spark configuration that was kind of rearranged, there will be a rearrangement of the spark configuration to make space for the newly appearing sparks or newly appearing, sparks basically. And during this rearrangement phase is where we are seeing this evolutionary drift mode behavior. So this rearrangement of sparks is happening, which is resulting in the basically the evolutionary nature of the drift modes. That's one proposition, possible proposition. Obviously, this needs to be further tested with this kind of pulsars, and that's what the future direction for this field is. Yeah. Okay. Next thing, I will quickly change a little bit of gear and talk about, instead of emission, I will talk a little bit about time. Pulsars are good clocks, right? I started by saying that. So because pulsars are good clocks, one thing we can do is we can look for those pulsars which are the best clocks. What does that mean? What does that means? Basically, the pulsars period for those particular subclass of pulsars should change very, 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 very little. And what are those pulsars? Those are something called the millisecond pulsars, because their change in period, what we call P dot, is order of 10 to the power minus 20. So that means they are extremely stable rotators, so stable clocks. Because they are stable clocks, we can use them for timing other things. Starting from effects of strong gravity to navigation in space, to the thing that I am interested in is nanohertz gravitational waves. So what are nanohertz gravitational waves? This nanohertz gravitational wave is supposed to be generated by the supermassive black hole mergers all across the universe. And the hypothesis is that there are many, many such supermassive black holes all across our universe at the core of the galaxies, and these are merging, and due to that, we are supposed to get these ripples of space and time. And because these are happening all across at different angles across the universe, we will get a combined background out of that, and which will happen in the nanohertz range. Why nanohertz range? We can discuss later. But what will happen is that from Earth, if we have a bunch of millisecond pulsars all around us, they will act as our detector, our observatory, because this the signals from these millisecond pulses is reaching us. But if this ripples from all across the universe comes in between, those signals from the millisecond pulses will be delayed, right? And that's what we are trying to detect. And famously, in 2023, the different PTAs came together and detected what is famously known as this curve, which is known as the Hellingsdown curve. What is the Hellingsdown curve? It basically measures the angular correlation between pulsars, distributed all around us at different angles. Now, if a nanohertz gravitational wave is passing in between us, then it will follow this kind of a curve of the angular correlation between these pulsars. Right now, by the way, disclaimer is, though this is consistent with the prediction, the level of significance is quite low. We are barely detecting. So our next goal is confirming this. Indeed, nanohertz gravitational wave is there. So, sorry. Gamma is basically the angular correlation between the two pulsars at two different directions. Residuals of two pulsars at two different directions.
Gamma, small gamma, 13.3.
This one? Okay. This is basically the spectrum of the signal that you would theoretically expect for this. That's the other layer. I don't want to go to this, but that's the. I can come back later. So basically, all the pulsar timings array in the world is basically trying to confirm this detection with higher and higher significances. But what does it require? That requires microsecond and nanosecond precision. Means the timing that you predict and the timing that you measure. The difference between that, you should be able with a precision of nanoseconds, which is not a joke given the level of noise, the level of RFI, the level of everything that we have. There are a lot of systematics to understand. I give one such couple of examples of those systematics. One is this. This is basically the dispersion measure, which is basically the dispersion the pulsar signal is experiencing as it travels through the interstellar medium. It's acting like a refracting medium, right? At different wavelengths. So the pulsar signal will be dispersed, right? Now we take care of that dispersion. The dispersion itself is not a big problem. But after taking care of the dispersion, whatever is this residual, that is being plotted here. And what you see is with different depths, it's doing this dancing. Why is this dancing happening? In this particular case, it's happening due to our sun. Mostly, effect of our sun. Because the sun is sending a lot of CME and a lot of solar flares. That is kind of adding extra particles in the path of the pulsar signal, which is making the pulsar signal delayed or changed. The other interesting thing is scattering, because again, interstellar medium, intervening medium is there. The pulsar signal for particularly these pulsars are very bright at low frequencies. Problem is that at low frequencies, the signal gets significantly scattered. And the scattering timescale goes as 10 to the power -4. So that means the lower the frequency, the larger the scattering. And you have to take care of the scattering. And we have some tools, we have some deconvolution mechanisms to descatter the signal, but obviously we see that our knowledge of the scattering behavior is still not complete. So when we try to deconvolve this, we understand, the knowledge of the descattering process or the scattering process that we have is not complete. There are a lot of gaps there, and our expectations and reality is not always going hand in hand. That is also. No, that is also there. Atmosphere is also there. What we call, due to atmosphere, we have significant, regions of scintillation particularly, and that kind of destroys the data. And it can be quite high in certain scenarios. Two things. One is when the scintillation is too high, we discard the data because there is no point. And to some extent, some ionospheric correction, scintillation correction is done when those atmospheric disturbances are low. And by the way, this is not complete. I am just giving 3 snapshots. There are a few other things. For example, if the pulsar.
Sun's pairs and things like that.
Yeah.
They are much more compared to the ionospheric changes in the atmosphere.
For the usable data. And then we have this. What is this? This is, remember, on the very early couple of slides, I showed an unorganized modulation, where the different pulses were different sizes. They were not just of different sizes and amplitude, they are slightly different in phase randomly and slightly different in width. So that's what we call intrinsic, variation of the pulsar's emission. This is happening due to what is happening at plasma level in the magnetosphere, or dynamic behavior of the magnetosphere. This is the intrinsic behavior of the pulsar. And whatever sensitive instruments you come up with, whatever integrations you do, this will not be away ever, to some extent at least. That is a big limitation. And here I would like to introduce the Indian pulsar timing array. This is a collaboration of different institutes where different faculties, PhD student, postdocs, master student, undergraduate students are coming together to work on the Indian pulsar timing array, which is basically looking at constantly monitoring every GMRT cycle a set of about 30 pulsars and regularly looking at their timing behavior to understand those systematics. So that we can correct for them at nanosecond level and then talk about nanohertz gravitational waves. And for that, we are using GMRT and UTI, primarily GMRT to be fair right now, but UTI is also going to be included. Sorry? SK is important, but I will talk about SK, but SK is yet to come up. So that's the reason. And for now, we are working with this. These are basically SK pathfinders. Pathfinders here. SK pathfinders. And yeah, so last year we released this Indian pulsar timing array dataset too, where we rigorously reported the timing solutions and all the systematics of all these 30 pulsars we regularly study with GMRT. And you can see here the dispersion changes, not the dispersion measure, but the changes in the dispersion measure are reported for these different pulsars. And again, the solar behavior you can see here for some pulsars, the sun angle behavior. Okay. Fine. But what we are trying to do in our group as a part of the NPTA is look at this intrinsic jitter behavior. But this intrinsic, dancing of the individual pulses in amplitude, in phase, in width, which we fancily call jitter. This is called pulse jitter. And this jitter behavior is the the primary roadblock to the high sensitivity, even SK observations, which are going to come up, because these will be very highly sensitive. So you can, take care of many other types of noise through modeling, but this is something what, it's very difficult to take out of. So when using those SK like very high sensitivity observations, you reach the actual nanosecond level. This particular jitter white noise, which is the intrinsic variation of the pulsar magnetosphere, will be the main roadblock to take care of, particularly for the bright pulsars. The jitter is the higher where the pulsar signal is more brighter. Okay, so here you can see the pulse signal is changing from pulse to pulse in amplitude, phase, and the height. So here what you see is basically the timing residuals after predicting the next arrival of the pulses and the actual arrival of the pulses. That's what we call timing residuals. And the orange one basically means if you take care of all the models, all the corrections, what we would expect the timing residuals to be. This is the orange ones. But the blue ones, what you see is the actual real ones. And you can see that the dancing or the scatter is much more in the blue ones, which is the observed one, which basically means jitter is significantly present there in those scatter. And one has to take care of jitter measurements, to get nanosecond level of timing precisions on NPTA. And what we are doing is my PhD student is basically looking at the jitter behavior of a couple of bright NPTA pulsars and trying to understand, are this jitter present to a significant extent? What is its frequency dependence? Is it indeed frequency dependence or not? And particularly if you see here for a particular pulsar, jitter at at high frequencies, which were reported earlier, which is mostly done typically till now, is much lower. But for at low frequencies, which is important for SK and pulsar observations, jitter can be quite significantly high. And not much studies have been done with respect to jitter till now, mostly because of sensitivity issues. But now we have GMRT, we can do these observations and get an idea of how low frequencies, how strongly affecting jitter is there. And that's what we are right now doing. So that's all about NPTA and short direction. Last few part of the talk, I will 7 minutes.
Yeah.
I will talk a little bit about the most exotic classes of pulsars, which is the magnetars. This magnetars, is very, very weird object. That's the only word for it. This has a magnetic field of the order of 10 to the power 14 to 10 to the 15 Gauss, which is the most strongest magnetic field in the entire universe. So that means when we study magnetars, we can understand how physics happens at this very extreme high, ultra strong magnetic fields. And these magnetars are not rotational powered pulsars like the other pulsars I have been talking about. These are powered by the strong magnetic field decay, like a dynamo kind of a thing of these objects. And they are mostly emitting in soft gamma rays and X-rays. And what we are looking at is this long-term behavior of these magnetars or flaring behavior of these magnetars. And the interesting thing is that till now only 30 magnetars have been confirmed. And these are mostly observed in X-rays or soft gamma rays. However, recently what we are finding is about 5 to 6 of them are also sometimes, not always, sometimes can be radio bright. Why is that important? Because that tells us two things. One is maybe a fraction of them is actually not like, exotically different objects, but connected to the radio pulsar class of pulsars, radio pulsar population of pulsars. They are not separate, but they are coming from a common origin. And we have proof of that because we have recently seen some magnetars which have switched off and suddenly emitting like radio pulsars, and vice versa. Some radio pulsars which have switched off their radio emission and suddenly started giving magnetar-like flares. Okay. So that's basically tells us, these two subclasses are connected. And secondly, recently there was a galactic pulsar, SGN 1935, which was shown to emit both X-ray flares as well as radio flares. Now, these radio flares were exactly looking something very similar to what we famously know as fast radio bursts. What are fast radio bursts? These are extremely bright radio emissions in like less than a second or millisecond level time scales. And typically, fast radio bursts are thought to be coming from extragalactic scales. But for that particular galactic magnetar, we saw that there was a first radio burst which was synchronous in time with that X-ray emission from that X-ray flare from that magnetar. So that basically means that magnetars are possibly one of the most favorable origin of FOBs, which is still an open question. So therefore, that gives us motivations to study magnetars which can be radio loud, or radio emitting. So for that, we were studying this long-term evolution of a radio loud magnetars in X-rays primarily, and then connecting it to the radio observations using geometry. And what you see here is that long-term, this was a magnetar which was active in 2003, went off for like many years, and then suddenly started reactivating in 2018. So this is a 2018 outburst. And you can see the long-term light curve of this 2018 magnetar. And at the very peak of the outburst, what we saw is the magnetar showed a very complex, it doesn't look complex, but if you model it, you will see that more than one harmonic is present. So very complex pulse profile, which kind of subsided to a very simple low amplitude pulse profile at the end of the outburst. So this is towards the beginning of the outburst, and this is towards the end of the outburst. And this shows the pulse amplitude. So pulse strength suddenly increases around the peak of the outburst and then slowly decayed. And at the peak, what we saw here is there was a complex profile where multiple harmonics was needed. What does that mean? That basically means at the magnetic pole, what is happening is that due to some internal shearing in the very strongly magnetized fluid, there is the idea, this is a proposed idea, is that there is a crustal cracking happening, a little bit like earthquakes. This earthquake is kind of breaking the crust and resulting in a sudden release of the magnetic energy that is stored here, which is resulting in the outburst. And that is enhancing the pulse amplitude here because there is a bright hotspot is forming where the crust had broken and a lot of magnetic energy has been released. There is a hotspot that is happening, and the hotspot may be not a monolithic hotspot, but a patchy hotspot, depending on how the magnetic field is getting twisted. And that patchy hotspot can emit very strongly at the peak of the outburst in this manner. and can be quite anisotropic. And what we see here, this basically, we have done a spectral analysis of this. Again, this is done by an MSc student. And what we see from the spectral analysis is that prior to the outburst here, only a two-component black body, two-component thermal emission was enough, which basically means there was some sort of surface emission and a very low-level hotspot emission around the pole. But near the peak of the outburst, there is a second additional component appeared where you have the strong peak. And that resulted in a very strongly hot thermal black body. Means there is a very hot anisotropic component that is forming in the pole, resulting in some sort of a twisting of the magnetic field. B dot D. This is basically the Maxwell's law. And yeah, complex initial some sort of a complex magnetic field twisting at the peak of the outburst, and that has resulted in the enhanced emission. And here, this particular phase is where the radio emission was also observed. So now what we are trying to look at is look at the X-ray spectral and temporal behavior from the X-ray, and then comparing it to the radio emission to understand when this anisotropy is happening at the peak and the hotspot is forming, how that is triggering the radio emission. So that is again an ongoing work. So I cannot give you the full answer because I don't know it myself. But that's what would give us a lot of clue about how the magnetar is cooling, and during the outburst, how it's turning its radio on and off. Okay. Now, because I don't have a lot of time, what I will do is I will skip over my LMXB part, and I will go to the end part. Sorry, I'll go to the end part and basically talk a little bit about two things. One is, what is the summary? The summary is that, as you can see, we using neutron stars. I primarily talked about pulsars today, but neutron stars in low mass X-ray binary systems can also be very interesting for studying the effect of strong gravity. And in principle, these can be very good, objects for studying, fundamental physics. And recently, we had many breakthrough results like gravitational wave discovery using neutron stars, which gave us an idea of the equation of state, the idea of the, how the mass of the neutron stars are distributed, and so on. There is recently some nicer results using the magnetosphere, or how the magnetic field of the neutron stars are mapped. That is some amazing new discoveries. The discovery of ULX pulsars, the discovery of jet precision as the neutron star rotates, and few other things. And I have put some things in gray to understand, these are not neutron star physics, but in principle, their physics is related to the discoveries of neutron stars. I have also talked about magnetar origin of FOBs and the evidence of stochastic gravitational background within PTA. So that means, basically neutron stars are really, really cool objects, using which, we can understand many different ideas of physics. And in future, what we have is a lot of missions that are going to come up. I particularly like to talk about SK. Thanks for mentioning this, because SK is starting its SUNS verification phase from next year. And which is basically, SK is, if people don't know it, it's the Square Kilometer Array. It's the radio telescope, multi-country radio telescope collaboration, which will be primarily in Australia and South Africa. And the SK LO is going to start its science verification phase next year. And with this radio telescope, with SK kind of sensitivity, we can test a lot of the open questions I kind of discussed today. So, and I am right now chairing the SK Neutron Star Science Working Group. So if you are interested in neutron stars and you are working in this field, please feel free to join the SK Neutron Star Working Group. Sorry for advertising this.
Opposite is part of the SK Science Work.
Okay.
So we are sort of part.
Actually partner.
So we can
I know that. I know that.
But not the neutron star.
But I am particularly advertising this because we are now starting some, some brainstorming to what can we do with the science verification phase next year, because the calls are going to come early next year. So yeah, so just wanted to advertise this. And in future, we have some proposed mission, some Indian proposed mission, even exact, which is something that people are now brainstorming. Daksha has been there for a while, and some international missions like EXTP and TMT from other wavelengths are also coming up, which will give us a multi-wavelength overview. I only give you a test of radio and a little bit of X-rays, but a multi-wavelength overview of all these objects can give us actual clues to how the elephant looks like, and many more exciting discoveries to come. Thanks.
Okay, so there were many questions during the talk, but if there are other questions, you just want